Thanks. Hello, Koome. Yeah. Do you hear me, Koome?
Yes, I can hear you.
Yeah. Hello, Magnus here. Yes, we. Hello and warm welcome to the first online Func Prog Sweden of the year. My name is Magnus and I'm the host and organizer of Func Prog Sweden. Func Prog Sweden is the meetup where we explore functional programming and functional concepts. And to further spread functional programming and give you more FP stuff, we have, as you might already know, started a Func Prog podcast. So please check that out also. And now we'll jump right into today's agenda. First, as always, short introduction by me, Magnus, and then we'll go over to functional JavaScript under pressure, from data transformation to scalable, predictable architecture by Koome Kelvin. Second presentation, functional Marmelade by Patrik Andersson. Yeah. First up, I would like to thank our video sponsor, Adabeat. Adabeat is a tech consultancy company where all the developers have a background in functional programming. And if you want to know more about Adabeat, you can go and check them out either on their webpage or on social media if you're interested. Then I'll go through the schedule for the coming spring, or at least the coming 3 months. So we have already hosted a meetup this year on 14th of January. We had a Scala winter meetup here in Stockholm, in-person meetup at Spotify. And today, 20th of January, we're on the online meetup. 17th of January, we'll have the next online meetup in February. And then on 18th of February, we will host a Haskell meetup at Scribe. That will be an in-person meetup here in Stockholm. So if you're interested in in Haskell and you are in Stockholm, please come and join us. Then 17th of March we'll be at Kivra in Stockholm, and we'll also send that live and stream it here on YouTube. So that's the coming schedule. And of course, finally, last but not least, last year we did run the Func Prog Conf, a half-day conference. This year we'll run it again on 14th of October. And today, this time around, this year, 2026, it will be a full-day conference, and we will host it and run it on Södra Teatern in Stockholm. So if you're interested, we will soon release the early bird tickets to that. So if you're interested, you should come and check it out also on that webpage. Now, to support Func Prog Sweden, head over to MeetUp, head over to YouTube, make sure to become a member and make sure to subscribe to our channel. And also, if you want to ask more elaborate questions to the presenters, please join Discord server. There are several places where you can find the invite to the Discord server, both on MeetUp and on YouTube. Already mentioned, but if you have questions during the presentation online, please use the chat, YouTube chat, or head over to Discord and ask the questions. With that, let's get started, everyone. So, first presenter, Koome Kelvin. He holds, welcome, Koome, to Func Prog Sweden.
Thanks so much, Magnus.
You're welcome, you're welcome.
Okay.
So, the stage is yours.
Okay, thank you so much. So, I'll jump into the first slide. Hello, you can hear me?
Yeah, we hear you loud and well.
Okay, so I'm going to the first slide, yes. Just a minute.
Voila, you're on your first slide.
So, okay. So, my name is Koome Kelvin. I have worked with JavaScript, using JavaScript for over 9 years. I've also worked with PHP and Laravel as a framework to develop web application. I've also built some tools that I will share later in this presentation. So today's topic is functional JavaScript under pressure, from data transformation to scalable predictable architecture. So what is pressure? Why pressure? So that is the first question, because why all this pressure? So you realize that when you're working with systems, there are three likely kinds of pressure that we are likely to face. So the first pressure is the data shape pressure that comes from nested objects and complex data. You also have the change pressure, which is found as a result of maybe updates which break changes into our code. And then, of course, we have the flow pressure, where big data, of course, as data becomes heavy, it is more harder to handle. So let's look at the data shape pressure points. So at the start of the system, you can see we are most likely to have a very simple system there. You can see users and simply an array of objects, no relationships, no complexity. Okay, so as the system grows, you realize that now the data has become more and more complex. You can see we have the roles relationship there. You can see we have nested objects inside each other and so on. So you realize that now as the system grows, then we shouldn't care, because the more the number of fields, the more the mistakes, the more the likelihood to make mistakes. Again, data shape pressure point again, the more the number of relationship, of course, the more the mental effort that is required to be able to figure out the nested objects and the relationship. Of course, as the data becomes more and more complex, it also again, it will require you to have more and more confidence to be able to dig deep into those nested objects and so on. So as the system grows, then problems start arising. For example, look at this code. You can see we are trying to fetch a theme from the first user object, which again has a nested profile, which has a nested preference, and then of course the theme there. You can see it's too deep. Again, that it's very hard to access. Again, you look at this other code here where in case we need maybe the usernames or maybe the names for our users in uppercase. Again, we realize that this map function will be repeated every other time within that functionality. So this one does not respect dry, don't repeat yourself principle, which is now something that is of concern. Again, let's look at this other code. As the system grows again, you realize that here we have an array of user objects, which in the first loop we are looping through to find the number of users, and then of course for every user we are going to the roles array again and fetching the roles and trying to output them. So you realize this code, the first thing, it is verbose. It's too large, it's too huge. Okay. Again, what if I forget an index? Errors start arising. It is hard to change. For us, for example, to add something like, let's say, maybe to add another condition, let's say, or another rule to the user roles, you realize that, again, the logic becomes tangled to these conditionals and so on. Again, this has to go in your mind. Of course, you realize high mental load because you must understand how these loops are going in, how they are solving things. Of course, again, you can see you have the state there, admin users. Again, state is, in this case, state is mutable. It's mutable, and therefore, of course, the more likely going to have errors. Again, let's see. How then do we solve the pressure? That is another point. How do we solve the pressure? So, of course, you can see here you have a normalized user, which accepts a user. Of course, down there you can see you are going through users.map, and then of course we are each user is then passed as the user there, and then of course we extract or we try to normalize these properties. So instead of going all the way to nested user.id, we just can fetch user.id using the ID property. Again, you can see, you can also say instead of user.profile.properties.theme, we can of course fetch that using just the theme, and we are good to go. So this becomes very easy because you realize that there's no complexity here. Again, data is pure, data is clean, okay? After transformation, after you have normalized the users, then let's see what happens. Of course, the nested data, which was very hard to access, the theme there, which is dark, again, it was very hard to access. Now, after transformation, of course, you can see now accessing it, it's very direct. Normalize users, again, the first item, and then, of course, .theme, the first user, and we are good to go there. So that is a tick. Let's see another example, grouping users by last login month. Again, now using the imperative way, of course, you can see again, you have a state variable there, users by month, and then of course you can see you have a loop, and then this loop goes through all the users every time. Of course, here the date, you have the date object, which of course is used to pass the dates. Again, we are grouping by year and month, and therefore, of course, you realize that we are getting the full year, and then we are of course using a dash, and then of course getting the month, and then of course if the users are not, or the users by month are not there, of course we are creating a new array, and then of course if the users by month exist, you are pushing the user to the array. So this is not very easy because high mental load, because you realize that these loops has to be in your hand, passing has to be inside the loops. again, you realize that pressure mounts anyway, because again, push imitates the user by month object. User by month, yes, it imitates the user by month, okay? Users by month, so which shouldn't be the case. So we will solve this using the functional approach. So these are next. We go to the functional approach, and let's see the function way to group users by the last login. There is, of course, here every object is standalone. The first is it's very declarative. It's very expressive. Get user, get login month. Of course, we are passing in the user there, and we are fetching the login month. For the other part, we are grouping using reduce, which now takes in, of course, an accumulator and, of course, the user. And then we are going to, again, we are fetching the month. And then, of course, inside there, we are returning. We are creating a copy of groups. And then for the month property, you can see we are grouping to check if we have the month. And, of course, if there isn't, we are pushing that user actually to the correct month. That's the correct maybe group by month, by year and month, okay? So this one happens to be very correct. View normalization. Of course, flattening data is what we have been doing. It's very good, but as we move on and on, things start to become complicated. For example, you realize that we have status there. A status can be, of course, a property, but it's an invalid state. It's unrepresentable because status cannot just be active, can also be a suspended, can be deleted. And as the status is active, then we realize that there are other required fields because it's active maybe from when, suspended when, for what reason, deleted at what time. So you realize that as we scale invariant states, of course, in case using the normal way, of course, the flattening that we did there, we may end up missing the property names. For example, active, you can see we missed E there. Of course, again, we are saying state data is not correct there. And of course, maybe it's not complete because again, we have scenes maybe for and reason for the suspended. And then multiple flags, of course, is true. We cannot have is active, is suspended, is deleted, of course. So normalization did solve state correctness, state transitions, and state completeness. So this takes us to this point. Data shape must encode rules, not just structure. So we can make use of the algebraic data types. We are now inside the users. Of course, we can create active, where we pass in the date, and of course, that's an arrow function that points out to return an object with tag of active and date. Suspended as well, pending verification. You realize that the required fields now are put there the right way. So correctness moves to data itself. Users.active, that is valid. Users.suspended, why, the reason and the date. Status.active, it's impossible now to have misnaming our properties. Change pressure point, change is inevitable. Feature requests will call for changes. Bug fixes, of course, will call for changes. State updates will call for changes. And we must know how to handle them. So let's look at this example, change pressure point. You can see we have people there, an array of objects again, and we have mutation, which is very risky down there because, okay, the first part is okay because we are filtering through the people, the people's array, and then of course we are filtering only the active ones. But the second part, active people mutation dot for each, then you realize that for these active users, then of course you're adding a point to them. But when we log the people, the original objects or the original array of objects, then it changed. Lona changed, but Koome and Martin points are mutated. Okay. original data is no longer safe. So the functional approach down there, you can see, instead of doing that, of course, we will filter, and then of course, we make use of the map, and then of course, instead of now mutating the people or the person, in this case, I'll create a copy of a person by the sprint operator, 3 dot then p, and then of course the points key, I will of course call the p dot points and 1. So that way I have not touched the original p. Of course, total points there again, you can see it. You are making use of reduce and so on and so forth. So you realize that the second part is the original array was intact. Let's continue. Let's do a deeper dive. User registration involves multiple steps: weak password, invalid email. For which steps you can fail, of course, email already existing in database, failed verification, failed login, and so on. So one of the things that we can do is to make use of the result-oriented programming, which of course takes two cases. It's either the result is okay or the result has an error, as you can see there. Okay. So the steps, of course, you can see the steps now become easier. You validate if the email and the password are okay. We check if the user exists. We hash the password and then you save. And then, of course, from there, you create a pipeline of functions using reduce. And then for success, of course, we run there, and for fail. And for success, you can see it's returning success and failure correctly, the way it should be. Flow pressure points. This happens when data goes through multiple transformation. We have to make systems predictable, of course. Avoid hidden state mutations, keep transformations explicit, and maintain testable pipelines. And to do that, of course, we'll make use of our transducers. Okay. You can see these are alternatives to using the map and the reduce and the filter, because we, instead of having arrays every other time inside the arrays, we will just have one complete array and do it like that. So I'll go now to the second part of my presentation, where we are going to see this live demo for the next few minutes. I think the next like 20 minutes. Pill code, you can see an orange there, and then we are peeling it. So I'll share my screen. I hope it's okay. So pillcode.devsip.tech. This is a site I created to help me and data developers, of course, those who are interested in functional programming, to be able to work their way up on it. So here we have that 3 challenges. I want in the next maybe like 10-20 minutes, we see whether we can be able to solve at least 10 challenges. So for every challenge, we have 3 sets. And of course, I'll try to explain it in the best way possible. I know how, on how I've used them again in my own project and so on. So the first part, of course, you can see here, we have an array transformation where we are required to double values. For example, 1, 2, 3 will double to 2, 3, 4. Again, we'll do it the functional way, where we will not mutate objects or arrays or for that matter. So here I'll make use of the map. And then, of course, I'll pass in a value. And then I need to multiply it by 2, like that, to make it, to double it. Of course, it will return an array there. So the other one, extract full names from user objects. Again, we realize here we are trying to deal with the data shape pressure point, because you want to extract the name. Here, John Doe. So again, we make use of the map. I'll take this map. And then, of course, we have user. And then user. Of course, we return. We make use of string literal there. and we return user.first, and then again user.last. Is it last? Yes. And then we close our map. Okay, a problem. Return users.map, of course, we have user.first, and then user.last. I put this outside. Okay, I'll run this. Good, moving to level 3. Convert prices to different currencies immutably. So of course here you can see we have a product, and the product has a property with an array of it's an array with items like name, price, and so on. So every product has this. So for us to do that, we'll go again through the map, and then we loop through every. I don't know if it's visible. I can make it a little bit balanced. So I will go through every product, and then for every product, then convert prices to different currency. So for every product, then we can come here and spread our product. Of course, I'll make use of an expression there. Again, it's inside that. It's inside, of course, this, I'll close this. The expression is inside, of course, we wrap it as an object. Let's see whether this works. Product, and then for the price, I will make it product multiplied by price times, okay, product dot price multiplied by rate. Of course, let's run this first. Good. So you can see here, you can have this is a use case that can be applied to different, let's say an e-commerce application where we have products and of course their prices, and we need maybe to run some conversions in terms of money and so on, to use US dollars and maybe euros and so on. So next challenge, let's see. Filter only active users. Of course, again, you make use of the filter. And then of course you want the user who is only active. I hope you are seeing how expressive functional programming is in JavaScript. User.active. That way we return an array of users who are active. Moving to level 2, filter product above the price threshold. Again, we'll filter, and then product. And inside here, you filter product dot price greater than or equals to mean price. Sorry for that. I'll run. Moving to level 3, filter by multiple conditions. Okay. So we realize that we want to send data that is already clean to the front end from the back end. So here, we can filter by multiple predicates. So the way we'll do this is I'll filter. And then inside the filter, we'll, of course, I'm filtering items. So let me wrap this inside item like that. And then I have predicates. These are predicates are simply functions that return either true or false, given whatever the process or whatever value is given to them. So predicate dot, I will use the every because, and then I will have every predicate or every function. So for every predicate, if it processes an item and returns true, then that is what we are going to return here. I hope you are seeing that. So inside here, we have merged filter and predicates. So here, predicates.every predicate, of course, predicate is the function and this is the end of predicate. So of course, at the end of the day, we must finish up or also wrap the item, the filter array method. Good. You can see, let's see how we are. We are at 6%, 2 out of 3. That's 3 challenges. We have 8 more to go. Let's see whether we'll finish that challenge very fast. The other one, sum all numbers. Of course, this now you make use of the reduce array method in JavaScript. And of course, we have number. And then of course, okay, Reduce takes in an accumulator in the number itself. The accumulator must also be initialized. So the first time we can initialize it to 0 there. And then of course, inside here, we can say accumulator plus number. I want you to note how I don't say plus equals, because I don't want the accumulator to be mutated. Accumulator remains for every loop or for every cycle, accumulator remains a new. So again, I don't have to modify the accumulator that was there. I create a new one, accumulator plus its number. Turn that, I will run the test. Moving to level 2, sum transaction amount. Again, we'll make use of the reduce. And then of course, we have the accumulator again. And then of course, transaction. And then inside here, we want to sum. So of course, it must start at 0 as the initial value. And then of course, here we want accumulator plus transaction dot amount. I hope that makes sense. So you can see, maybe we may require maybe in an e-commerce application to have a sum of all our items that we have bought, all the items that the user has bought. So I'll run this. Moving to level 3, calculate average with reduce. So here, the first thing I'll test for is I'll test for edge cases. So because I cannot, for me to calculate average, I must calculate the sum of numbers and then divide them by the length. So here, I will make use of numbers, or I say numbers, again, make use of an array property called method. If numbers.length happens to be equals to 0, then I will return 0 because we cannot have an average there. Otherwise, I'll go to numbers, return numbers.reduce, accumulated value, and then number. And then, of course, there we can see we want accumulator plus number starting at 0, and then we divide this by numbers.length. So I'll run the test. Good, I created 3 of them. Let's continue. I hope you're enjoying this. Get unique values. So JavaScript, or functional programming JavaScript, allows us to have a set method that allows us to have a unique value. So here, I'll return new set and then pass in my array. Okay, there's a problem because I added one dot the spend operator. So I'll run this. Set is capital. Again, case sensitivity, good. Get unique IDs and sort. So again, here, the way we have done before, new set, and then of course IDs, like that. We returned it and wrap it into an array, and then of course sort, apply the sort method. Moving to level 3, unique objects by property. Here, we want unique objects by property. So it's a little bit complicated, but you look at it well for the next few minutes. So here we have items. So inside items, we want to return unique objects by property. So here, if it is by the key, let's say key is ID here. So we don't want duplicates. We want to do the duplication, of course, which will now handle the data flow pressure point, so that as we send data to the system, it is data that will not make the system to lag. It is data that is clean and data that we want to, that is required for the system. So here, I'll make use, the first thing is that I will map, and then I'll map through the item, through each item. And as I map through the items here, I want to return 2 values. I want to return a tuple. And the tuple that I want to return here is item item key and the item. Okay, so having done that, then we realize that we must pass this through the map for us to get unique key value pairs for this, or not key value, but unique tuple, tuple items. So new map, of course, I'll come and close it here. And then we must wrap this inside an array. And then inside here, inside the new map, of course, okay, I almost confused this. So map item, this is the for the map, then this other one is for the map in the outer part. So inside here, I'll call the values. Maybe I will first of all print these items, and then I'll call the values iterable so that I can be able to get this. Let's see whether it works. Good. So next challenge. Of course, this handles the duplication. There's no duplicates. We remove them. Next challenge. We are at 3. We have how many more challenges to go? We have number 4. Let's try and see. Flatten one level. So to flatten one level, I will call nested.flat here. That flattens one level. Flatten and increment each value. So here I'll call flat. And then, of course, what it returns to me, I'll call map. And then I'll map x to x plus 1, like that. Moving to level 3, deep flatten in nesting level. So here, I will call nested dot flat, but now a flat to infinity. Of course, another function away, run. Good. Let's go to the next challenge. Merge two objects. So here we are merging two objects again to one. So we can make use of the sprint operator in JavaScript. And of course, we merge that with object number 2, like that. I missed B there. Moving to level 2, merge an array of objects into one. Merge an array. This is an array of objects. So anytime we hear the array, of course, we must remember the reduce accumulator and then the object. Of course, objects dot reduce accumulator object. Of course, we must initialize it first to an empty object like that. And then inside here, I'll pass in an expression here that will come and sprint accumulator and merge it with the object. I hope this works. Whatever you already have stored plus what we are adding a new run. Moving to level 3, good. Deep merge objects recursively. So deep merge object recursively. This is another one, which is a little bit technical, but we'll look at it very fast. So the first thing here, you want object 1 can contain nested and nested and nested properties. Object 2 can contain nested and nested and nested properties. So here we must apply recursion so that we go all the way and merge only objects, not any other data type. So here I will come and have an array. Maybe I'll check for if something is an object first. So for me to check if an item is an object, what I will do is I will come and check the first thing that it is not. Okay, this object, of course, I will pass in the value, and then I'll come and check, is this not, it should not be an array. So an array will give us an array, so we'll check whether it is not an array. And then we'll check type of value. If it is equals to an object, we are good to go. Then we'll also check if type of object is not equals to null. Because in a null is an object, so we don't want to test for null. So having done that, I will expand this a little bit. So deep merge recursively. So here, I will come and return object.keys. There's an array method. There's a method maybe to fetch keys inside objects. We can make use of array keys. We can make use of object.keys. That will return for us only the keys, an array of keys. So here you can come and spread object1, and also you can come and spread object2 like that. So remember, object.keys only accepts one object. So this one will merge the two into one. And then from there you call the reduce. And then when you call the reduce, of course it will pass in the accumulator. And then of course you have the key, because it's an array. We'll be going through these keys each every time. So inside there, of course, I want to return an initial value. Initial value will be an empty object. So that is okay. Let's now continue. So inside here, I'll come and calculate value 1 first. So value 1, I'll come and call object1, and check whether this object1 has a property called key. Okay, because the key itself here will be these items, the items that we pass in from here, the keys. So if object1 happens to have a key and it is not, okay, if object1, first of all, why we are using the question mark and the optional chaining here, it's because at times we could be having object1 being null, and if it's null, then we want to return its undefined null. So again, I'll come and call again constant value 2, and then I'll call object number 2 again. I'll check whether it has a property called key. So here I missed 2, so I will go back and put my 2 as a property 3. So inside there, very fast, let's see. So inside here, we want now to come and call the accumulator key, and assign it to, of course, the accumulator key will assign it to number 1. We'll check whether it is an object, whether value 1 is an object. So we come and check is object value 1, and also is object value 2. That's when we'll be interested in merging. So we'll have a question mark there. If it is an object, then of course we will recursively call solve and value 1, and then value 2. And then if it is happens, of course, the ternary operator, if it is not true, so we'll overwrite. So we return value 2. And if value 2 does not exist, then of course that's when we return value 1. And then inside here we return accumulator. Let's see how it goes. I hope it works. I'll run an expected const. Just a minute. Let's try to debug. Just a little bit. Const accumulator key. Oh. Unexpected token const. I don't know where that is coming from, but it's live coding, so just a little bit because of time. Let's try to debug. Okay, const is object. Here it passes in a value. You are passing in your array is array value, and type of value is equals to object, and type of object is not equals to null. And then return object keys, reduce const value 1 is object1 dot key. Sorry, dynamic properties there. we need to access this one's dynamically run. Just a minute. Unexpected token const. Is this const the one that is making us have all these problems? Oh, this const is object value 1, value 2. So let's use let me use let here, and let I see whether we are missing an argument list somehow. We are somewhere. So inside here, of course, here inside here we should have opened this and closed it here. And then we run, but here should be const, not let. Const, because we don't want to keep these things to keep on changing. Const, let's see. Yes, good to go. Next challenge. Because of time, how many challenges? Yeah, 6. Let's try and see whether you get there. Index item by ID property. So here items, you want to index them by the ID property. So here, we want to go through items dot reduce very fast, accumulated value item, and then we'll call this expression there. These items is an object, so I will just leave it as an object there. So you want to index it by ID. So if I want to index it by ID, then of course I'll come and spend the accumulated value, and then I want to index items by ID. So here we have so we can have item.id. That one will give us the ID, and then of course we can come and spend the item. I don't know, but if that works. So I'll run this. Oh, assign it the item, sorry. Yes, I was almost forgot that. Index by a custom key function. Again, items.reduce, accumulated value. And then of course we have the item. And then of course our expression will go there and you initialize it to an empty object there. So again, we spend the accumulator, but now instead of passing in the key, you pass in the key function and then pass in the item. And then of course here we will pass in, we spend that with the item. Moving to level 3, index with value transformation. Again, items.reduce, accumulated value item. Again here, my expression goes there. I like doing it like that and then initializing to an empty object. And then inside here, I'll come and spend the accumulator. And then we have the group function. So dynamic properties here, group function. This group part or key function, key function, which is the group. And then of course I'll pass in the item. And then this one will be assigned to the value, which will be returned when item is passed into that value function passed in there. So I'll run this. Next challenge, group by category, very fast. Again, return items.reduce. So inside here we have the accumulator, and then we have the item. Again, my expression, which I love so much there. And then inside here, empty object. So here, we want to reduce by category. So the first thing is that you come and spend the accumulator, of course, and then you want by category. So item.category will be given by, now it's where it gets a little bit tricky because we must first of all spend the accumulated. We check whether in our accumulated or in our store, which has item.category, you come and check whether something is there. If there's nothing there, we create a new array. Okay, so this one here, you come and wrap it inside an array like that, and then we wrap it again here, and then of course that's when we merge it with our item. So I'll run this. Moving to level 2, group by custom grouping function again, reduce accumulator item. This is very expressive in JavaScript, like that. And then inside here, of course, you come and spread the accumulated values that we have. And then here we have the group function, which will give us the key. So we pass in the item in it. And then inside here, of course, we make the same song and dance, accumulated group item. If it exists, if it doesn't, we'll create a new array and put our items there. So this one ends here. This one ends there, and then item, and then of course we wrap this inside our array. So run this. Unexpected, should be like that. Group is not defined, group function. Run. So group function should be a function. So like that. Good. Moving to level 3. Group and transform. So items dot reduce accumulated value item. And then of course inside here, the same song and dance. Like that. Accumulated value, you spend it. And then of course here again, dynamic properties. We make use of the group function and then item. And then this one will be assigned to what? To be assigned again, the same song and dance. We spend the accumulator, accumulated value. And then the key itself will be the group function item. Or if it doesn't exist, we return an empty or return a new array like that. And then I put it moving the other side. So I wrap this, and then I'll wrap again it here. And then inside here, I'll come and have my item, but this item now must be transformed. So transform function, and then the item. Again, this is of course handles change because we are passing in. So I'll run the test. Good, cleared. Next challenge. Create a pipeline of functions executing from left to right. So here we have value. So you pass in, you call the functions dot reduce accumulated value, and then the function itself. Function, of course, reduce executes left to right, and then reduce right to left. So here function, and then of course you have the accumulated value, and then of course the initial value will be the value there. Moving to level 2, create a reusable pipe function. Reusable pipe function. So this one will be again FNS functions dot reduce accumulated value, and then function itself. And then of course here you call the function the accumulated value, but the values must start at X. So run this. Moving to level 3, create reusable pipe function, the same song and dance that we did. I think this one repeated itself. Reduce accumulated value item. Okay, accumulated value, and then of course I like calling this, I can call it function because it's a function. And then of course inside here we'll have accumulator. I'll call the function and pass in the accumulated values, and then they must start at X. Clear. Next challenge, carry an AND function. Of course this is A, you carry, maybe you have 2 items there, you can carry A plus B. run this, moving to level 2, carry 3 arguments. Again, because we have here already, you pass in B, an arrow function which again passes in C. So here it will be A plus B plus C. That's what it will return. Moving to level 3, generic carry function of linearity. Let's see how this works. So here, I'm receiving arguments, an array of arguments. And then, of course, what I'm trying to check is, are these arguments dot length, are their length equals to, greater than or equals to the function dot length? If they happens to be equals to that, then of course I will pass in the arguments and execute them inside the function. Otherwise, if they are not, I will call the other more parameters. Okay, but now you can have this, you can call it carry. You can maybe define it as carry. So next here, next again, you can come carry there and then spend our arguments first and then spend our next operations like that. So run this. Oh, we didn't return carry. So here, return carry like that. Next challenge. So I think 30%, then that is okay. So I'll go back to my presentation. So I think this is okay. I hope you enjoyed it. If you would like to look at it, also just type devcip.tech functional programming in JavaScript. Okay. Just a minute. Fill code. Just a minute. I think I typed the URL wrongly. Fill code.devcip.tech. Good. So here you can see the functional programming challenges were here, like that. You also have closures. You realize that when you are passing everything again, remembering what is outside it was very important. So you can also try the closure challenge. And by the way, I also have a book here. You can look at it. I have also another site I created called codeshoots.devcip.tech, where again, all the screenshots you see for that presentation I made, I created them using this codeshoot.devcip.tech. So you can choose also the themes there and see what happens. I don't know. So you can see that. Okay. So I think I'll go back to my presentation and finish up with that. Of course, you can see here we have the three. Please check out them. The site I built to help developers practice functional programming. You can see I've solved 10 out of at least many challenges. You have solved them there. Again, this will boost your confidence on functional programming in JavaScript if you are interested. I also have codes on tara.devcip.tech where I share software development insights. There's code shoot where I just shared how I created the screenshots for my code. And of course, if you liked whatever I did, you may look at the book here that I created for JavaScript at LeanPub. Yes, I think that is the end of my presentation. I hope you enjoyed it.
Thank you very much, Koome. Thank you very much. And as always, as I say to everyone, it's very brave to live code also. It's also tough. It's always tough and you always end up in some error or missing some kind of parenthesis, comma or something, and then you're staring at the code and where is the fault? Where's the fault? Where's the fault? Super stressful. Well, yeah, thank you very much. How come you come into FP style of coding with JavaScript?
Yes, come again, please.
How come you started with functional programming in JavaScript? Well, I mean, what was the reasoning or thinking behind that?
So JavaScript actually I love it so much. I've worked with it severally, and it supports many functional programming methods. Okay, so having had a background with JavaScript, I chose to go with it because of my background. That is. Yeah.
Yeah. Yes.
Yeah.
When did you come in contact with functional programming?
The first time I heard about it, I was in the PHP community.
Mm-hmm.
And I heard a talk by Andersson on curing the common loops. So from there I was hooked.
Okay, nice. How long time have it taken for you to write all these like examples and everything? It looks very extensive.
Yeah, I have always written them and refined for the last 2 years.
Oh, okay.
Yes, but I will keep on adding based on the challenges I meet.
Cool.
Yeah.
So if you're like,
you can see the.
Yeah, please go on.
Yeah, you can see I'm here to implement the asynchronous and the monans and the transducers, but I will implement them with over time. Yeah.
If you're like an imperative programmer, where should you start in JavaScript? Like where you are? Like, do you have that on your web page? Like how to start using immutability, or are there other ways to start if you're like new to the concepts of functional programming within JavaScript?
So maybe what I would recommend first, maybe for someone who is new to JavaScript, is maybe to look at the foundations first, because things like spread, array methods, they come in handy when it comes to creating functional code. Again, I created a book on that. But of course, after that, you can maybe try more deep challenges, like the ones we have been doing here, and that will at least boost someone's confidence. Yeah.
Thank you again, Koome, and thanks for your presentation. As always, we'll output all the and we'll publish the video, and then we will, once that's done, we'll also put all the links and everything in show notes and whatnot in the comments or in the description of the YouTube presentation, so anyone can find your the challenges you have and your web page and publications and everything. So again, thank you very much.
Thank you very much, Magnus. It's a high privilege, actually, being the first presentation 2026. It's a high privilege, and I look forward to more.
Thank you.
Yeah.
Thanks and goodbye. Then
goodbye.
Thank you. We will now go over to our next presenter and our next presentation, Functional Marmelade by Patrik Andersson. Patrik Andersson, you welcome up on stage or into the camera. Yeah.
Thank you.
Yeah, you're welcome. So today we will hear you discuss, or not discuss, but present your own language that you actually written. It's very impressive. Yeah. Yes, I'll hand over the stage to you, and you're welcome.
Thank you very much.
Yeah, welcome.
Good evening, my friends. I have made a thing, and I'm continually making this thing. Let's start my presentation. Is this presentation on now? Yeah, there it is. Functional Marmelade. Because if you make a programming language, you get to name it. And I actually started out with another language, which I decided to call sylt, which is jam in Swedish. And since this language is functional and the first one is not, well, this is clearly more sophisticated, so clearly it's marmalade and not jam. And it's a yak shave, of course. I mean, who's going to use it? My name is Patrik Andersson. I am a functional programming freelance, and I would describe myself as a person that is compulsively drawn to things that I don't understand. such as programming. I thrive in trying to learn new things all the time. I started out as a professional or self-professed Java programming expert, I should say, which is, I don't know, you can read from that what you wish. Maybe I had conflated two things, which is whether or not I was a competent Java programmer and whether or not I was knowledgeable to the level that I thought back then. But then, luckily, a friend of mine showed me a programming language called Scala sometime in 2009, which is a long time ago now. Now, of course, at that point, I thought it ugly, so I didn't pick it up. But the year after, 2010, I started learning Scala. And with that came general functional programming, and I was progressing through languages such as Haskell, F#, category theory, lambda calculus, and lots of things that I didn't even know existed, which to me was something that I dearly needed. Let's call it an ego death. It brought me down to earth in a way that I truly needed that. And I would say that at this point, I am honing my Rust skills, which is my latest, let's call it, love. But why? Why would you do that? And I would say that because of my unbounded curiosity, I really wanted to learn how this works. I mean, how do you do it? We use compilers all day long. How do they work? That and the fact that I wanted to become really good at Rust. And it's not impossible, so I might just as well be the one who can do it. I should try it. And the one way that I know to do this is to try. Try to do something that's difficult to do, but it's not impossible to do, and then sticking to it for a really long time. I mean, eventually, if you make progress every day, you're bound to get somewhere. And the language that I made before, called Sylt, is imperative, and it does not have a type checker, but it does have a number of other things. So I thought to myself, well, now I have a rough idea what these other things are. Let's see if I can find some more about this. So I wanted to implement a type checker, because that seemed very hard. I did not understand how they worked. I mean, it's not difficult to think about what the type of 4 is. I mean, what type is 4? It's an int, of course. But what about a function that accepts a 4 in the third position? What type is that? Well, I know what type it is because I can do functional programming, but how does a typer find this out? I mean, if you start to think about it, you realize that if you have a program, a long program that calls something, passing plenty of deep expressions into these parameters, how is it going to sort that out? How, since I was the main character in this plot, how am I going to sort this out well enough to be able to write a compiler that does it for me? And then I wanted the language that would do currying and functions as values. And finally, in using the language, I wanted the full Jungle Monkey experience, which I'll attempt to explain down the line, further down. So, what is the recipe for such a thing? Make me a functional language. Well, I did it in the spirit of the MLs, the ML languages, such as Standard ML, OCaml, F#, Haskell, because to me, that's the way they should look. But I wanted a more regular look and feel, as in different types of things don't look too different from each other. They look more similar than different. And the core theory behind it that I wanted to use, although I didn't know it at the time, because at the time that I started this, I had only heard the name, and that is System F. So I wanted the core the core foundation of it to be systemf with sum types, with product types, and recursive types. And when I started doing it, I also added, or I made sure that its let binding are polymorphic, which we can become theoretic if you want to, and have rank 1 types. It has explicit parametric polymorphism with implicit instantiation, which is a mouthful. What that means is that you can have a polymorphic function, which is to say that it accepts a type parameter, but you do not have to supply them when you use the code. They just appear, or they appear to the compiler. And I wanted all the fancy Greek symbols because it looks good, clearly. So there are very few surprises, and we can see here by regular I mean that, well, there's a name, start. This is a definition, and it's assigned something. It's assigned something that prints something. And it says lambda there, which is just, well, it's a function. And you can say this in a number of different ways. And also, at least this is my opinion, in the spirit of MLs, you do not have to supply type annotations. It will infer all the types. So, that was wrong. It will infer all the types, so it will infer that the thing is an int, which we can see with our eyes, but the compiler can too. And it can see that show has a type for all A, which is to say that, well, you can give it anything, and it will give you a text. And it infers this by simply comparing the different things that you throw at it with the definitions that it already knows about. And there is one type error. In this let another thing, we can see that it's trying to add an integer to a string. So we get a type error because there's a type checker and it refuses this. On the one hand, in my left hand you gave me some text, and in my right hand you gave me an int. I don't know what to do about that, so it's an error. And it's at least superficially inspired by lambda calculus, and which is to say that the syntax follows the usual way that we present lambda calculus. So for instance, there's the fancy Greek symbol lambda, which is synonymous with the word lambda. So when it says compute earthiness, it accepts the radius of Earth and it computes the volume of this sphere. Well, unless you are of the opinion that, well, maybe there's an ice wall because Earth is flat. And we want to account for this so that people can actually compute this scientific fact by passing a flag that indicates whether or not you think there's ice walls. I don't know. And the Einstein functions that we all know about takes 2 parameters. And the way you tell Marmelade about this is by providing 2 parameters exactly the way you would in, I think, Haskell. And the language is also white space significant, the same way both Haskell and F# is, but OCaml is not. And by that, if we look at the right column, we can see that it binds 3 to pi for reasons. And in the in block there, we can see that anything you put in the same column belongs to the same block. And this is the reason why pi is 3 and not something else. Because there are no floating point types at this point. Because there's only 24 hours a day, and I didn't add floating point yet, which I'm going to. And of course, you can add type signatures, which I am of the opinion that maybe you should, at least for top-level values, which also happens to be the only type of declaration that you can annotate with a type signature at this point. And the way that we draw type signatures is the same curried way that we do in Haskell, and it's very similar to the way we do it in F#. So there's an arrow, which is a right associative operator, which means that if you supply one parameter, it returns a type, it returns a function that is the remainder of the type signature. So going back to the Einstein function, we can see that it accepts two parameters, m and c, so that means that there's two int arrows as well. And you can make your own if. Let's call it whence. Because why not? But there's also the usual serving of Boolean algebra. So you can use if you want to, and there's and or, XOR, but there's no not for the same reason that there's no floating points. You can write it yourself. I can write it for you, but I haven't done it yet. Seems to be a theme here with Earth being flat. I'm sorry, but there's also a helping of the usual, as I mentioned in the start, sum types and product types. So there are tuples, and all you do is separate expressions by a comma, and that forms a tuple. There's also string interpolation, which has its own slide, but you can see there that just backtick something and you can put any expression in there, any expression in the whole language. So you can write your program in there if you want to. And there's pattern matching, which we can see here. I'll get to that as well. And there's also co-products, which is a fancier term for some products. Perhaps there, I wanted to be fancy. I didn't go with the usual option or maybe like the more common languages do. Since I'm the one using it, let's go with perhaps. It's funny to me. Which is to say that perhaps is a type constructor. It accepts one type parameter A, and it has two constructors, this and nada, which is completely isomorphic to option. So this is some and nada is none. So assigning this to order number infers the type perhaps text, because it's given a text and it's called through this. So for instance, let's say you make a divide function, you want to divide two numbers, but if the divisor is 0, well then there's no defined result. How do we solve that? Well, if let's just return nada to indicate that, well, there's no result for you to have. Otherwise, it wraps it in this. And the type inferred for this is it accepts two ints and produces perhaps an int. There are more co-products. This is the one slide that I have that gets quite theoretic. This is the way the typer sees things. So in the previous example, the perhaps type and the call to this, it goes something like this. So the type is the same perhaps, and the little weird upside down A there is pronounced for all, and it means the same thing. They are synonymous, even though actually they're not. This is an error on my part. It's actually a type lambda. But I was under the impression that these are the same thing for the longest time, so I haven't had time to fix it. But what it does is that first it evaluates what's called an apply expression on 2, where it applies the constructor function this to the literal 1, and the type of this function, the type of this constructor, is on 3. So the type is a value of any type, the alpha, from the type former in perhaps, and it produces a value wrapped in perhaps. Perhaps it produces a value. And what the typer does when it sees this 1 in the place where its type signature expects an alpha, it's that it tries to unify them. Because, I mean, if you, in the same place, say two things about one thing, well, I have to unify it somehow. How do I do that? So the little tilde thing there in the braces, that's theoretical mumbo for unify this. And the result of unification is a set of substitutions, which is maybe a little hard to swallow word in this context, but what it produces is a list of instructions. It says that every time you see alpha, you should put int there. So, in 5 there, that says, apply these substitutions that I have on my left side, that alpha is supposed to be int, to the type expression on my right side, which is the type constructor perhaps applied at the type parameter alpha. So the result of this is that, well, every time I see alpha, I should put int there. So the result is that when you do this, give it 1, it infers the type perhaps of int. And this is only one of a number of rules in the typer. This is the rule for apply expressions, the one at point 2 there. There are similar rules. They are not identical. They are in fact different for different types of syntax constructs. So for a variable, it's going to look in something called the typing context, sometimes referred to as the gamma. For a binding with the same name as the variable, because it expects that, well, if you're going to refer to a variable, you better have told me about it before. So the typing context is going to contain that the variable Charles has the type int, or it has the type a type parameter. And the type for, let's say, a pattern match. What's the type of a pattern match? Well, it's going to look at what it is that you are trying to pattern match in some expression, and provided that it finds the pattern that matches, which it is going to do, then it's going to find the consequent, like, what do you want to happen when this pattern matches? What type does that have? Well, that's the return type of the, and so on. There are 20 different rules at least. And this is the magic that makes what I started out saying, like what happens to a function call when you put 4 in it in the third spot, but there are deep expressions on all other places. This is another very common or very, very known co-product, result. Because I want to be fancy, it's not called OK and error or left or right. It's called return or fault because it's my language. And it works the same way you would expect any of these result types, which is called either in Haskell. So if you say return 10, which corresponds to, say, OK in Rust, or right in Haskell, or Scala for that matter, then the type of a function that does this is going to be result of int and some unknown type for the error. Because unless there's more context, how would it know? And the same goes for bad times, but the other way around. You tell me that there's a failure, so now I know what the failure is, but I do not know what your success type is. Let's repeat the divide function again. it starts out the same way, takes two int parameters. It does the same check. Is the divisor 0? Because in that case, then clearly it can't be a result. But this time it's a little bit more informative. So it tells us that Mr. or Miss, there was a division by 0. There's no result for you to have, but this is the reason why. More product types again. Records, they look pretty much like any old functional language. There are some small tidbits here and there. They can of course be polymorphic, so after that double colon equals there, you can put a for all, and you can have any number of type parameters you wish, and it'll work. So let's talk some more about pattern matching. This, in my opinion, is a core tenet of functional programming. So on the left we have, let's call the function switch for maximum confusion. This one, a lot of things is happening here, even though it's a quite small example. It scrutinizes, as we say, x, and on the left-hand side of the column of arrows, it compares x to 1. If that's what it was, then it returns 1, and then 2, and then otherwise it's not a keyword. You can put anything there. It's a catch-all. And the type that the type inferencer deduces for this is int to text. And the reason for the int there is that there's an inferencing rule for the deconstructed syntax node that can infer that since you are comparing x to ints, then x clearly has to be an int. And if x is an int, then the lambda x is also an int. So the rule for a lambda is also, it looks inside itself to see, well, what is my own function doing? What does it accept? And what does it produce? Well, it produces a text because we can see that to the right of the arrows. So, as we can see, calling switch with 2 produces 2. And then we have this pesky citizen, the sovereign citizen, which compares x to 1, the int, am I being detained? And then it compares it to a string. Well, what's it supposed to do there? So what happens is that in my left hand, we can't worry too much about what's left and right here because the order of things in the typer can be anything. But in my left hand, you gave me some text, and in my right hand, you gave me int. I cannot unify this. There's no way for me to produce substitutions that say that, well, you should look at this type parameter because it's not even a type parameter and substitute it with int. It makes no sense to say that every time you see text, you should put ints there. So it doesn't type. There's a type error. And this is one of the things that really made me want to write a functional programming language, because look at the right side there. That pattern match is humongous, and it's deep. So if we go back to the left column, where the data types are defined, we can see that, well, movie has an acting lead, whoever that is, and there's a sidekick. So already there's some sort of, well, maybe there is, maybe there isn't one. And if we look at actor, the actor can also be known for some other movie, which means that if we squint a little, like Clint Eastwood in The Lights, we can see that this clearly forms a recursive list. So this pattern could be, there's no limit to how deep it could be, because the also known for movie can contain an actor, which can contain an also known for movie, which can contain an actor, and so on. We've made a recursive list, a recursive type. This is no problem for the typer, this is no problem for anything, and most of all, this is no problem for the pattern matcher. And this, to me, I mean, when we look at the pattern match to the right, we can very easily convince ourselves that, well, that makes sense. I can see what that does. But how do you how do you program that? That has to be some arcane dark magic going on underneath. And until you've actually successfully implemented one, well, who knows? Maybe it is. And there are two very important properties of a pattern match. The first one is, at least for a typed language, the first one is if we look at this deconstruct, we have to imagine that make1 produces a value of this type, dollars. So there are three fields, the good, the bad, and the ugly, of course. Sorry, we have to look at it some more. If you look at the field called the ugly, you see that there's a perhaps there, which means that this type can have two main categories of values. There could be a value, could be this 5. There's also the case where there's no value, could be nope or nada. And this pattern match doesn't take that into account. So if you look at the assignment to the ugly there, it says this ugly. But what if the field value is nada? So this pattern match is not exhaustive. And part of the type checker, I don't know if it is technically a type checking thing or what it is. It's part of my my pattern matching logic. It's going to blow up and be angry and say that, well, your deconstruction does not cover all of, and then it just refies the expression in there. And we can see that, well, the remaining constructors that you have not accounted for is that. The empty parentheses is just, well, it's ugly printing, that's all. But if you look at the ugly, it says nope. You're not telling me what to do if there's a nope in there, so this program is going to crash. So therefore, if you want a total program that type checks, this clearly should not type check. It's not exhaustive, but they should also be useful. And this is an example of that. So let's say that the first match clause that you provided is, well, otherwise 420. That's going to catch everything. Then what use is there to have some specific match clause after it when, well, you have already caught everything? And this, I mean, you can be very strict and say that this is an error because it seems to me being the compiler, that you had an intention there and your program does not seem to match what I think your intention is. So please correct it for me. Because the other clause there, it's not useful. It doesn't add anything. This, all functions, we call it that they are curried. What we mean by that is contrasted with a language like Java or C#, which accepts a single parameter list, which we can, if we squint our eyes, consider to be a tuple. Whereas, so you have to provide, if it takes 4 parameters, you have to give it all 4. There is no choice. Whereas in a language, in a functional language that has curried functions, you can partially apply a function by providing a subset of all the parameter values. So for instance, map, which accepts 2 parameters, one function from A to B, and some sort of value. Since my language does not have higher-kinded types, this map is specifically for the data type called perhaps. So you give it a function and you give it a perhaps value. But if you provide only the function, then map still calls. There's no problem. But map returns a new function. And this new function is a function from perhaps A to perhaps B, with the first parameter already bound in the environment. So when the implementation of map runs, eventually, given the second parameter down the line, f is already in there. So when we look at the section where it says lambda f and xa on the first signature, that is, in a sense, syntactic sugar for the second definition there of map lambda f period lambda xa period. It's a lambda that produces another lambda, which we could, if we wanted to, call it a mapper or something. And all functions are lambda, so these are two different things, although they are always used in this. Let's not get caught up. The way that I did Marmelade is that I made it easy on myself and the compiler, and I say that all functions are lambdas. There's no special case that is a top-level definition or anything, so it's completely regular that way, which is to say that all definitions, top-level or not, are values. You can do whatever you want with them. You can put them in a map, you can pass them as an argument, you can say them whatever you want. And they can be recursive, which is actually surprisingly, I don't have a slide for this, which is surprisingly difficult, because a lambda or a closure contains an environment which is a fancy name for a hash table with one entry for every binding or every variable. But for a recursive function to be able to call itself, it has to have its own name pointing to itself. But it doesn't exist yet. I'm in the process of defining you now, so how am I to provide a link to yourself to yourself? So recursive functions are recursive. And the same problem repeats itself, pause for applause, in both the typer and the interpreter and something else that I forgot. And text interpolation, we've already seen some of this. So in a string, my name is, etc., you can put backticks. And inside these backticks, you are free to have any expression you wish. You can call functions, you can have if statements in there, you can have lambdas in there, you can do whatever you want. That's between you and God. Do whatever you want. And to show this, they are actually also infinitely recursive. So the string can contain backticks, and in the backticks there can be another string, and in this string can be another set of backticks, and you can just go wild. So, coming sort of closer to some sort of conclusion, let's make a list, because what is a functional language without lists? This slide tells the story of two things. First of all, list, called just list, is a polymorphic type, which is to say that the list itself is just a structure, and since you say and promise that, well, it can be the structure around anything, it's for all alpha, but it has the same shape and structure as the int list and the text list. But the problem with those two is that you cannot write functions that accepts any list if there are only concrete lists, like in a language without generics. And this type is, did I say that? This type is recursive. So a list is either nil, which is an old term to say, well, it's empty, it's nothing, like null, I guess. Or it's cons, which is an old term for, I think, construct. I'm not completely sure. You can construct one node of a list by providing a pair of two things. First, some value that you wish to have in your list, and then the rest of the list, which we can see there. It says cons, alpha, and then in parentheses it says list of alpha. So you can cons 1, and then in parentheses cons 2, and then in parentheses cons 3, etc., and then nil. This is the same way it works in basically, deep down, the same way it works in basically any functional language. And the way we deal with these is that it's customary to deal with them in terms of heads and tails. So if we start out with tail, which is probably the easiest function, it deconstructs the list into either a cons, which is to say a node with a value x, which we're not interested in the case of tail, and the tail. So return the tail, or nil, because, well, the list was empty. And we say, denotionally, I think we call it, that the tail of an empty list is also the empty list. But what about head? What does it mean to say head of a list of 1, 2, 3? Well, you get the 1. And the head of the list of 1, you also get the 1. But what about the head of an empty list? Now what? So we put some more code in there. Let's bring back our old friend, the perhaps type again. And we redefined head to say that, well, head no longer produces the element type. So the type signature of head is no longer list of A to A. It's list of A to perhaps an A, because maybe there isn't one, in which case it's going to say nope instead. And then we have map, a very ordinary function, and some Greek letters, because I get to have Greek letters if I want to. And the definition of that is to say that for every cons node in the list, let's replace the element, which is called x in that case, with whatever f transforms x into, and then we call ourselves with the same function and the tail, called x's. And if it's nil, it's nil. This means that if you were to call map with 1 plus, that means that it's going to invoke 1 plus x on every node and produce a new list. Same with length, which, if we squint our eyes again, it looks sort of similar. It deconstructs the list, and if it discovers a cons node, well, it adds 1 to the length of the rest of the list by calling itself, just like map. And if we try it out, we can see that ahead of a cons node is this one. And the type of this is perhaps an int. And the head of nil is nope. But it's not a nope or perhaps int, because how would it know that your empty list in your mind is a list of int? It doesn't know, but it promises to be very helpful for you. So if you return that in a function that promises to return a perhaps of int, it's going to infer the type int for the nil as well. But as we can see, the structure of map and length repeats. They are very similar to each other. And in the way of functional programming and other programmers as well, we don't like that. So this is called structure elimination, when you traverse some structure and you produce something else that's probably less complex, but that's not necessary. So what we do is we extract the logic of traversing the structure or whatever we had. So we still do deconstruct into cons or nil, but this time we ask the caller to provide us a function f that has the signature a to z, and z is customarily the type that we assign to the accumulator. And then we ask that the caller provides an initial value of this accumulator and the list that we wish to traverse. So what foldWrite does then is that it transforms the first element that it finds by combining it with the accumulator, and then it continues with the rest of the list by calling itself. Exactly like we did for map and length here. So we have, in a sense, captured the actual process of traversing something and given it a name. We call it foldWrite. And the reason we call it fold is because we can sort of think of it like we write a list of items on a piece of paper, and then you could fold one fold for every item on the list and make like an accordion of it and look through it. And then we redefine map and length in terms of this fold right instead. We can see that not only is it smaller, it is also that since we now have this deconstruction in only one place, and the array of functions, map and length, is not just 2. It's 50 functions that you may want to do on lists or similar things. Since they are constructed in terms of simpler components, it's easier, at least, not easy, but easier, to convince yourself that your things are probably correct. There are reasons why we call it fold right as well. I don't know if we have time. I want to get into that, but there's fold right, there's fold left. It sort of depends on how, in which order, let's say, that you traverse the data structure. But we're going to talk about golfing. Let's not kid ourselves. There's a lot of repetitions in this too. If we have a look at this example, call show. It says that, well, I'm going to call show. And to be able to call show, I have to provide an X to show. I don't have an X. You have to give me an X. So call show is a lambda. It's a function that accepts an X and returns whatever show accepts. And returns whatever show returns. And if we look at the type signature of call show, we can see that, well, it's the same type signature that show has. And clearly, since all it does is call show, it clearly does the same thing as show does. And this, in lambda calculus, is called that, we say that the first example that is in, I don't know how you pronounce that, eta expanded form. And these can be reduced. You can just remove the X, the lambda X, and remove the parameter to show and partially apply show, because it's the same function. It doesn't add anything to ask for a parameter just to pass it on. We could just return show immediately instead. It has the same type. And what happens then is we're going to golf it all the way now to 9,000. If we look, this is at the one there on the left column. We can see that map. It has the same signature that we saw before. It calls fold right. It asks for a function, and it asks for the list in excess. And it passes them right through. So the first thing we can do for 2 is the same thing we did here. Remove the lambda x, remove the x. So if we look at 2 compared to 1, remove the x's from the left side on the lambda former and remove it from the right. The function is shorter. And we can go one step further if we look inside the function past the fold right. It asks for the x, which is the element it folds over, and the accumulator, which we call tail. But it passes tail on. It doesn't do anything with it. So we can reduce it in there as well. Just remove the parameter, because what happens is that cons there is partially applied. And by doing that, it has the same type as the function expected by the fold right function, so it's shorter. And then for 4, for actual maximum effect on the golfing here, it would have to have the Haskell operator, the little ring. You would say cons ring F, but I don't have that operator yet. So we'll call compose. I mean, this is just for show. There's no reason to do this. I mean, I do it anyway because that's, I don't know, it's funny. And then the same thing with length. This is, don't do this. And this is where it gets interesting, because look at, first of all, they are all written in some sense, in some way, in terms of fold right. There's no pattern matching in any of these. even though this is a list, which is a recursive type, it has two constructors. So clearly something else is looking at these and scrutinizing them and doing the right thing, and that is fold right. So any error we could have done there, they can't happen because it's already taken care of. And when we have append, which appends the first list to the second list, done by fold right quite elegantly, which is to say that the right-hand side list is the accumulator. So just prepend the first list to the second list. And then bind, or flat map, you can call it that as well, it does the same thing. So for every element, it calls the function on that element, which gives it a list, as we can see in the type signature. Alpha produces a list of beta, and that's a list. So append that list, and then fold right. You have bind. And when we have bind, we can define filter in terms of bind. But what we need is some sort of predicate to know which element do we wish to keep in this list. So if the predicate says that, well, this element is a keeper, then make a list out of it. If it's not a keeper, well, make a list then too, but make an empty list. So if we look at bind, the definition, you can see that it does append. So it appends an empty list, does nothing. So when you filter a list, and it says that, well, I don't wish to keep this element, it appends an empty element, which is nothing. And flatten, which is a list of lists, you say that every element in this list is a list. And if you bind it, you say that, we look at the bind signature, we say that, well, alpha is a list already. And since I am asked to provide a list, which is a list of beta, and I already have a list, I just pass it through, which means that it's going to concatenate all the lists into one instead. None of this is going to be in the exam. But this way, you can continue. I mean, you can make zip, which I was going to do, but then I didn't do it. But doing zip means that you have to have bind and map, and now we have bind and map, but yeah. You can continue writing these combinators, and they are all this short because it's functional programming. It's excellent. These are the resources. So early last year, from sometime, well, maybe quite literally, exactly 1 year ago, I started writing Marmelade. And I continued up until sometime May, when my son was born, and after that I didn't have more time for it. But then late autumn last year, I sort of started again, but I didn't want to continue in the same repository because I had a number of new ideas of how to improve some things that didn't quite. It was difficult to make it correct, let's say. So I did it a different way, and I think I worked very well. So the second repository is where I do all the development these days. And everything is written in Rust, which is a wonderful language. I mean, it's not F#, but it's still a wonderful language. And the Jungle Monkey. What I wanted was that when I use it, I wanted the experience of being a monkey in the jungle, and someone comes up to me with a mobile phone, hands it to me, and like, have you seen this? That's what. And I don't know. I kind of have this. I kind of have that experience when I do it, because for instance, when we did the code golfing, I mean, why does it work? It looks like advanced math. How does it figure it out? I did this. How does it? I mean, how is it? I can't understand how it's possible, even though I wrote it. It's weird. So I've succeeded in that. And the same goes for the pattern matcher. Actually, since it's recursive and it can do all these things that when I look at it, it's trivial. I can see what it's supposed to do, but it does it as well. How does it happen? So, yeah. that's what I had. Thank you very much.
Thank you very much, Patrik. Thank you very much for your presentation. Yeah, thank you very much. Again, lovely presentation. When you said, like, I always thought when I studied at university that I wanted to write my own language because it was so cool to write your own compiler. Then you start looking into compilers and then you thought, no. Then you said something like, but I can decide how the language should be, how it should look and what words to use. And then I thought, well, maybe I should
Yeah,
go back
exactly.
again.
That's a good ring to it.
It is.
Yeah.
Yeah. But you said you started with Sylt.
Yeah.
Yeah. And when was that? Was that a couple of years
That
ago?
was not too far before that, maybe half a year before, actually.
Yeah. Okay. And was it also written in Rust?
Yes, it was.
Okay.
So all of this, since the last couple of years, have been very, very focused and targeted at becoming, honestly, very good at Rust, because that's what I want. So I gave myself gradually more difficult tasks. So I started out writing a Redis client, then I made a Redis server, and then I can't remember some other bigger, more difficult thing, and then I made Sylt, and then on my spare time, so that, yeah, doing my best to educate myself, basically.
Yeah. How and so the reason to do this in Rust was that you wanted to learn Rust more, or was there other reasons? Like
More
Rust was
twofold, because I mean, I've always been very fascinated by parsers, because, well, I don't know, honestly, but there's something kind of magic with the fact that, it understands what I write. How does it? I mean, I wrote it just now, but now it works. That's weird when especially when you feed it input that is recursive, and it still figures it out. That's just very clearly very fascinating to me.
Interesting. We had one comment in the chat that said, like, they like the word of use perhaps instead of
Yeah.
It is a nice word. It is a nice word. When you do design of a language, do you sit and think like this will be funny, or this will be useful, or this is just the way I want it?
I mean, of course. I mean, I'm a big child, so of course it has to be funny. But at the same, I'm sort of fascinated by languages generally. So I do, even when I program in common languages, I do really spend time thinking about naming, which we all do, and I do that too.
Of course.
I think it should look good. So there's no person manager, because that feels boring to me. What's it called? Well, what does it do? I really spend some time, because later it's a communication tool as well. So I guess that ties into what it is that fascinates me enough to actually write a compiler too.
Yeah. So what's the next step here? Will you continue with Marmelade?
Yeah. I've been at this, not all of, I mean, mentally, let's call it, all of 2025, but I didn't have time half of the year because of my son. But I'm going to continue. There are lots of avenues that I wish it had. For instance, I would like to have type classes. There's also an aspect of type checking called bidirectional type checking that Marmelade has, the old, which is to say that you, from the bottom up, infer the types, but you can go top down as well and say that, well, this must be an int. So I'm going to check and make sure that it is an int, so you sort of meet halfway. And in different areas of the typing process, there are pros to doing this. For instance, you can very easily say that there is a type error, because if you infer, it's going to say these two, they don't go together. Which one is wrong? I don't know.
No.
They're not compatible.
No. Interesting. I'm just checking the chat here. People are saying thanks for your presentation and thanks for introducing to a new language. Yeah, it's really nice.
Come help me if somebody wants to.
Yeah. Absolutely.
That will be fun.
Yeah. And I guess we can put out links to the repo and people can download it.
Yeah.
Yep. final question. Would you be, I mean, I don't know, this is purely speculative. Like, what if someone wants to contribute to your Marmelade? Would they be welcome?
Yes, of course. Yeah.
Yeah. So people, take a chance.
No.
Join in.
Very interesting.
Yeah.
Yeah.
Yeah. Cool. Then thank you very much, everyone, for watching. And thank you, Patrik, and thank you, Koome, for coming on. And that will be all for today, tonight, or tomorrow, depending on where you are in the world. So thank you all for coming, and thanks again, all the presenters. Until next time, have a great time. Cheers.
Thank you very much.
Yeah.